What is the most used man-made material on Earth? You guessed right, it's concrete. Look around. It's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. And welcome to another episode of the Concrete Logic podcast. And today I have Peter Paone, Director of Engineering from ZAP Engineering. Peter, could you tell us a little bit about yourself?
Sure. I've been working in the cement and I'll say related minerals industries for the last 21 years. I graduated from Lehigh University here in Bethlehem long time ago with a degree in chemical engineering. And I went and I started working for a company called FL Smith, which is a Danish company, and they supply equipment primarily to cement plants. So I had experience doing engineering and doing process design work. So actually kind of fitting all the pieces together in these plants that make cement. And I'm sure all your listeners know cement, not concrete. So all the kiln systems, all the milling systems, I would help design a plant for a certain production and for a certain type of cement. And then I had a unique opportunity because I'd go back and forth between designing those plants and then commissioning them. So I'd go out in the field, discover all the problems with them and try and get them to actually run. And then I'd come back and I'd normally switch back and forth between designing new plants and doing research and development on trying to make them better. And a lot of my focus on my last couple of years there was actually on emissions control. So things to reduce NOx and SOx and mercury, a lot of these different emissions that the EPA, tries to cut down on from cement manufacturing. And then I left there in 2012, and I've been doing consulting work in all sorts of different cement and minerals plants out there. Done quite a bit of work with pozzolans and calcine clays and whatnot, but I'd say most of my focus over the last 20 years has been on cement.
Nice. Yeah, so we connected via LinkedIn, of course, because I reached out to our followers, our Concrete Logic followers, after I read this article that was in ENR about, here it is right here. I'll just read the title here. EPA revises cement, steel emissions requirements and final good neighbor rule. And I was like, oh, what is this? So I started reading about this good neighbor rule, and apparently this is something that has a focus on reducing the NOx emissions, and they specifically called out cement manufacturing or cement plants, and that got my attention. And I was so focused on carbon emissions that I guess I wasn't paying attention that we do things like to reduce our NOx emissions too. So I was like, hey, we're just now trying to figure out how to reduce our carbon emissions. What's this new thing? And as I read through it, it's not new. It's something, I guess, and Peter, you can correct me here, but it seems like this is something that the EPA looks at it's looks like every 5 years or so. Is that a correct statement?
Yeah, most people have probably heard of the Clean Air Act, which is really the law that tells the EPA that they have to go out and they have to periodically make adjustments to the rules to try and improve air quality. So one of the key things that they are told that they have to go and improve, it's not actually NOx, it's ozone. And probably a lot of people are familiar with the ozone hole, so they're aware of ozone from that. But, the ozone hole and the ozone layer in the atmosphere is a couple miles up in the air, up in the upper atmosphere. What the EPA and what most people are more concerned with is ground level ozone. Ground level ozone, if you have asthma my wife and my daughter both have asthma. Sometimes you see those ozone alert days when you're getting the weather report in the morning. Ground level ozone, can cause some serious health effects for people who are asthmatic, who have difficulty breathing, like the elderly. And it's not normally just found. Normally, ozone on the ground level is created by really complex chemical reactions between a bunch of different pollutants. And NOx is one of those key pollutants. So the reason that the EPA gets into regulating NOx from these sources isn't because of the NOx itself. It's because it's a precursor. It's something that creates ground level ozone.
I got
so that's
you.
why they get in. That's why they get into regulating it.
I got you.
And it's really an alphabet soup. And what I mean by that is there's all these different regulations that kind of lead one on top of the other. So when I do training for people, I do training for the Portland Cement Association. When I do training for cement plant operators and environmental engineers and those sorts of people, I talk about the alphabet soup of all these regulations. And one you hear about is the NAAQS, 5 letters, National Ambient Air Quality Standards. And what those standards say is you have to maintain a concentration of ground level ozone below a certain level. So when I was growing up, that figure was up around 100. And over the last, I'll say 20 years, that number has slowly been brought down to 90, down to 75. Sometimes you'll hear about things like non-attainment and attainment areas. These are areas that are either in compliance and actually meeting those targets, or they're not. So most people are probably familiar with what these regulations mean by your inspection stickers, right? One of the things that the states do is if they have non-attainment zones for ozone, they try and get vehicles off the road that emit more NOx and emit more soot and things like that. And they do that through the emission stickers on trucks and on passenger cars. So that's one of the results of those standards that you're now seeing that we're talking about as far as applying for cement and power plants.
Right. Yeah, each state has their own standard, right? So the EPA is kind of the umbrella over it. Is that
it's kind of strange how it works because the EPA doesn't issue permits. So when you have a cement plant, it's not the EPA that issues the permit for the air. And particularly for your car or for your truck when you're driving down the road, you're not getting a permit sticker from the EPA. The EPA basically empowers all of the state governments. So if you're in Pennsylvania like I am, or if you're in North Carolina has to submit a plan to the EPA telling the EPA how they're going to achieve compliance, how they're going to meet these standards. And one of those might be saying, look, in these counties where the ozone level is too high, we're going to have inspection stickers, and we're going to have emission stickers on cars. And in these other counties where we're not worried about it, we're not going to do those stickers. So that's part of the plan that each state puts together to tell the EPA, this is how we're going to achieve compliance with this new limit that you have.
But they can the EPA tell? I was, again, trying to understand these standards within this. Can the EPA say that their standards are not, I guess, to the highest or to the level that they want, and then they overrule their standard? Is that going?
I don't think we've seen that yet.
Okay.
The states individually will go to the EPA and say, here's my plan to achieve it. And this good neighbor rule that kind of started all this discussion is really one of those ways of, I'm trying to think of the right way to put it, but it's trying to, I'll say, assist some of those states with pollution sources that are coming from across their borders, right? So a lot of ground level ozone, a lot of ground level NOx is caused by cars, but some of it's caused by big, we call them stationary sources, cement plants, power plants. And what part of this rule is trying to do is to help downwind states, downwind locations deal with emissions coming from other states that are pushing them potentially over their ozone limits.
Gotcha.
Hopefully that makes some semblance of sense. I mean, the whole thing is complicated and convoluted, and certainly not very easy to follow for someone who hasn't followed it for a long time.
Yeah, no, like I said, once I read this article from ENR, and then you click on the link to the actual page where on the EPA has on EPA.gov, and you open up that page, and there are lots and lots of links to click on. But there's if you go to, for the folks that are listening, if you go to EPA.gov and search Good Neighbor Plan, for, I guess this originated in 2015, because it says for 2015 ozone, NOx, what you mentioned before, Peter, NAAQS, and it's got the map, and it shows the states that are that fall under this plan. And what's interesting is so, like I said before, that it's only some states, and only some states have to follow the rule for both their power plants and other industries, which would the cement kilns would fall under. And then some of the states are just for the power plants, and then looks like just California, for some reason, is the only state that is covered for everything but power plants. So it's definitely if you got some time to waste, it's there's a lot to read in here, which is interesting to me, and that's why I wanted to bring you on here. But can you talk a little bit about so if we were just to look at the NOx emissions, the different kiln types, can you talk about that and how they're imposing different limits on depending on the kiln type? Does that make sense?
It does, and maybe it helps to talk a little bit about how cement's actually made as opposed to concrete. So cement is, I like to tell people, it's not just one compound, right? There's a lot of different types of cement out there. Mm-hmm. There's in the U.S., I mean, there's at least 8 different main types that people talk about. 1 and 2, and not so much 2, but 3, 4, 5. You have white cements. You have all these different, masonry mixes, and a
favorite on the podcast is Type 1L.
Type 1L, and then you'll probably start seeing a lot more Type 1P and Type 1T as some of these carbon rules come into effect. So you have a lot of these different types of cement. As a cement manufacturer, as someone who's making cement, it all comes down to the chemistry. So you're trying to make a blend of a certain amount of calcium, silica, iron, and alumina. Those are your 4 main minerals that kind of go into making whatever type of cement you're really aiming for. To do that, we take, normally it's limestone and a bunch of other materials, and we melt them. So we grind up huge amounts of rock. You can see entire mountains disappear over time as you're quarrying out the rock. But you have to heat up that rock to the point where it physically melts. My kids just get fascinated by me showing them videos of making lava in a kiln. Mm-hmm. Because that's essentially what you're doing. You're trying to control a location and making lava. And then after it comes out of the kiln, you cool it off, and you grind it into the cement powder that all everyone's familiar with and normally misidentifies as concrete, right? It takes a tremendous amount of heat to melt that rock. So the rock coming out of the kiln is going to be somewhere around 1,450 degrees C, so that's upwards of 2,600 degrees Fahrenheit. Certainly, I would not want to be inside the kiln at that point, because it's probably a little toastier than I want to experience. But all of that heat does a lot of strange things to the air and to the fuel. At that high of a temperature inside a kiln, the nitrogen and the oxygen in the air. So air is normally just about 80% nitrogen and 20% oxygen. It's 21% oxygen by volume, 79% nitrogen. At those temperatures, the nitrogen and the oxygen will physically react with each other. Like they'll break apart and they will reform as NOx at those temperatures. And certainly the higher the temperature, the more the air decides to react with itself. So that's really where you get some of this NOx formation in a kiln system, is just by heating the heck out of the air and causing the nitrogen and the oxygen in the air to mix together. So the oldest style kilns out there, you see these wet kilns and these long dry kilns. They take up a lot of fuel. They use a tremendous amount of air. They normally have a very high amount of NOx that's just naturally emitted because of the way they were designed. You know, when rotary kilns were first becoming a thing 120 years ago, no one cared about NOx. They were just looking to improve upon some of the older technologies and make more cement. So they tend to be, I hate to call them, but NOx generating machines. They make a lot of NOx just by the nature that they've been made. Mm-hmm. Over the last 20 or 25 years, we've seen technology change where now you hear about calciner kilns. And I think that's one of the things you have listed in that rule. You have calciner and you have preheater kilns.
Yep, those are two of them.
Right. So starting about, back in the 1950s and 1960s, cement manufacturers, or I should say the equipment providers to cement manufacturers, started coming out with preheaters. So the old days, you had a 400 or 500 or 600 foot long kiln, and all of your reactions took place in that one piece of machinery, right? Mm-hmm. So you had to preheat the material, you had to dry off all the moisture, you had to start breaking apart some of the clay components in there, and then you calcine the material. So the limestone you're putting in there, calcination is just a fancy way of saying we're boiling the CO2 out of the limestone. And you'd have a heating section, and then you'd have a section where you're melting the rock. So if you look at a kiln as a series of reactors, it's 5 or 6 reactors end to end. It's a preheater, it's breaking apart the clays, it's doing some more preheating, it's calcining, doing a little more preheating, melting, and then surprisingly at the very end of the kiln you have a small cooling zone. So just right where the flame is starting is actually colder than at the heart of the flame. So as you get down the kiln length, material actually starts to cool off towards the end, and that's where your clinker minerals start to set. Right, mm-hmm. That's where all those minerals that we're trying to create start to crystallize and grow and make what we're aiming for in our cement. So these older kilns, all 6 of those processes get done in that one single tube. Back in the 1950s and 1960s, a couple of these OEMs figured, you know what, this isn't very efficient. If we can separate out some of these reactions, we can make it a lot more efficient, use a lot less fuel. And really what we're trying to do is squeeze more toothpaste out of the tube. You have a 600 foot long kiln. It's a lot of maintenance on something like that because you have 6 supports. You're trying to keep them all in a line. If you overheat them a little bit, the kiln starts to torque. You start getting these funky shapes on the shell, and no one ever likes that. So they started introducing what people know as preheaters. So they came out with a couple different designs where now this material you bring into the preheater, you start to heat that material separately using the gases that you're producing in the kiln, but you can control the speed a little bit different. So now we can improve how we're heating the material up, and maybe we're not wasting as much of the heat coming out of the kiln, right? So we burn less fuel, we get more of that heat into the material. And then around the late 60s to 70s, they started introducing a calciner. So now you've got a preheater that's preheating the material. You've got a calciner that its only function there in life is to just drive CO2 out of rock. So now by splitting all of these different processes, you essentially split the fuel that you're using in a kiln system in half. And I mean that quite literally. You drop the amount of fuel that you're using in the overall system in half. So between industry and these OEMs, I don't want to say inadvertently, but they've helped improve the emissions from these systems over time just by being able to reduce the fuel consumption, right? Well, a couple bright people back in the 90s came up with this concept that if you can burn the fuel that you're using to calcine the material just right, you can actually use that fuel to get rid of the NOx that you're creating in the kiln. So we call them reducing conditions, right? So there's two different ways you can run something. It's oxidizing, so you have a lot of oxygen available, you have oxygen combining with things, or reducing, which is normally when you have too little oxygen, right? So we call those reducing conditions. If you put a little bit of fuel in there without having enough air, you burn, and I'll use a fancy term that no one's going to understand, substoichiometrically. Really fancy way of trying to make me look smart by saying you burn it with not enough air to actually burn everything out. What that does is it makes a lot of hydrocarbons. It starts making all these funky carbon monoxide and hydrocarbons and all these sorts of things. And I'll use a wrestling analogy. All of those little hydrocarbons, they are desperate for oxygen. They don't have enough oxygen to burn. They are looking anywhere they can to steal oxygen from something. And all this kiln gas that's coming into the calciner has all this NOx, which, as we talked about earlier, it's got nitrogen, it's got oxygen attached to it. So it sees the nitrogen connected to the oxygen. It says, I want that oxygen a heck of a lot more than that NOx does. And those hydrocarbons basically put the NOx in a chokehold and rip the oxygen off of the NOx and leave behind nitrogen.
Huh.
So with this way of staging the airflow and staging the fuel flow, they've come about this way of making a lower NOx system. They basically use the fuel that they're firing to reduce the NOx that's being made in the kiln. So it takes a special way of doing that. Like, you actually have to design the calciner in such a way that you can put the fuel in without having enough air in. And you have to do a whole bunch of things to make sure it mixes well at the end, or else you wind up with a whole bunch of other stuff you don't want. But long story short, you're able to use the design of your kiln system, of your calciner, to reduce the NOx by itself. So if you look at that rule, you'll see the long kilns, the wet kilns, the long dry kilns, you have a higher limit. That's because you will just naturally always have a higher emission level out of those kilns. Mm-hmm. You get into preheaters, you might have a little bit lower level, and you get into a calciner design. If you design it just right, you can get a very low NOx coming out of that system to begin with.
And do they combine? And then are there systems where they combine the preheater and pre-calciner?
Yeah, so normally if you have a pre-calciner, you'll have a preheater right after it. That's not always the case, depending on the design of the system, but that's, I'd say, 95% of them out there.
Gotcha. All right. So that makes sense why they have, based on kiln type, they have the different limits listed here.
So that's just with the design of the kiln, right? So that's going out and designing the equipment to try and keep the NOx as low as possible. The problem that a lot of plants have is, I mean, you build a cement plant, you're expecting it to run for 100 years. You're not putting up a cement plant and then 20 years from now turning off the keys and shutting the doors and saying sayonara. Mm-hmm. So you've got plants out there from the 1950s and the 1970s and the 1980s that weren't designed in that manner, right? So now you have to get into all these add-on technologies. And I'd say that's probably another reason why you have those tiers of different emission levels, because most people use, and I'll throw out some more fancy terms, either SNCR or SCR for NOx control. And I'm saying, when I say most people, I mean beyond the cement industry. Those are the two technologies that most people talk about. And they're both fancy ways of saying we're going to spray ammonia or urea into the gas to get rid of NOx, right? I'd say most people are probably more familiar with SCR without even knowing it, right? If you have a catalytic converter on your truck, on your car, That catalytic converter is a catalytic reactor. So SCR is selective catalytic reduction. If you've got DEF on your truck, if you've got a little DEF tank that you're using, that DEF is basically urea. It's being sprayed onto a catalytic reactor, and it's being used to reduce the NOx from your truck. So a lot of people probably are familiar with the technology, even if they don't know the fancy terminology for it. So a lot of industries use SCR. A lot of power plants use SCR. And like I said, it's just a fancy way of saying we're going to use ammonia or use urea to reduce NOx. It requires a lower temperature, but it requires a very expensive catalyst, right? So you spray the ammonia or the urea on the catalyst at the right temperature, and the urea or the ammonia react with the NOx to get rid of it and form water and nitrogen, which everyone's okay with emitting. In a lot of cement plants, we don't use SCR. We use SNCR, which is a fancy way of saying we're going to do the same reaction, but without using a catalyst. The reason we don't like the catalyst so much is because, number one, it's expensive. And you need a lot of it because cement plants have a lot of dust in them. You know, by the time you get your SCR reactor in a truck, the gas coming to it's normally fairly clean. It doesn't have as much soot. You've got a lot of dust that can react on the surface of the catalyst in a cement plant and basically kill it so it won't work. So most often what we're doing is we're using SNCR, where we're injecting this ammonia, very high temperature, again, trying to get it to react with the NOx and get rid of it. So a lot of plants in the U.S. currently use SNCR, so they'll spray in a solution of ammonia to get rid of it, get rid of the NOx. The problem is that it's not nearly as effective percentage control-wise as SCR. So you can get rid of maybe 50% of the NOx, maybe a little more with SNCR in a modern kiln. In power plants and some other facilities, you can get upwards of 90% reduction with SCR. So the catalyst can get rid of more, but we have, some pretty substantial hurdles to get it to work in a cement plant.
Yeah. So where do they you explained it as like a bolt-on technology. So where do they bolt this on? Is it within the kiln itself, or?
So with the SNCR, you can spray it inside the system. So for long kilns, for long dry, long wet kilns, it's really a fun project when I've had to work on them. You have to figure out a way to get a tube that's stationary into a big rotating kiln, because you have to get it at just the right temperature zone. And that temperature zone in a long kiln is like halfway down it. So you have to figure out a way to get a tube to the end of the kiln and then mate it up with the rotating section. So you have this special coupling on the end. You take it through the coupling, which comes inside the kiln, pops out the side wall of the shell, and then runs along the kiln shell down to the right temperature zone, where it comes back in and you have a sprayer, right? Not nearly as effective in wet kilns because you don't have as much control, right? You can't really move the nozzles once the kiln's spinning and once everything's installed. You're kind of fixed in location. So that's how you do it in a wet kiln or a long dry kiln. In a modern preheater, precalciner kiln, you have a little bit more control because you can work around the outside of it because you're up in the section where there's nothing moving. It's just the vessels. In those areas, you're normally having a couple spray nozzles, and you're trying to get the ammonia in just the right temperature range. So when I do training for people for the PCA, I talk about time, temperature, and turbulence. You certainly need the right amount of retention time. It's got to get in there. It's got to react before it starts to cool off. It's got to be at just the right temperature range. And there's an optimal temperature range of somewhere around 1600, 1650 with ammonia, maybe 1800, 1850 F with urea. If you don't find just the right temperature range, you either burn up the ammonia. So at too high of a temperature, you actually generate more NOx. At too low of a temperature, you get slip. It goes through the system without reacting. And then you have all sorts of problems with the ammonia coming out the tailpipe and basically coming out the stack and causing visible plume issues.
Ooh.
So that's how we do SNCR commonly. SCR can be done. That's normally done at the exit of the preheater. Like I said, that's a little problematic because there's a lot of dust at that location. So when you're doing SCR on a cement kiln, you need a lot of catalyst. You need a lot of space for it, and you have to do a lot of things to try and control how much dust builds up on the catalyst. So it's not nearly as popular here in the U.S. as it is in some other countries that help subsidize it.
Huh. Let me ask you something. You mentioned back in the 50s the cement manufacturers, they came up with a better solution, a more efficient solution, and then again in the 90s they did it again, and that wasn't driven by government policy, right? Those two events.
No, it was primarily driven by I'll say cost, right? So one of the big drivers of, I'll say, adoption of technology has been, the cost to operate. One of the biggest drivers was the oil embargo back in the 70s. The cost for oil drove a lot of cement manufacturers to try and reduce how much oil they were using. Mm-hmm. So taking out older kilns or modifying older kilns to try and reduce the fuel usage was driven primarily by trying, to remain in business. They didn't want to be driven out of business by more modern plants that were having a lower operating cost.
So was the industry before this good neighbor? I'm sure everybody knew that this was coming since they've been working on it for 8 years. But has the industry been doing anything as far as becoming more efficient that by doing that it would reduce the NOx emissions anyways, or are they? I'm just listening to you explain how those two and I can't remember those acronyms again, but those two ways of basically spraying ammonia into the kilns and everything. It's very problematic. It sounds like, and I'm just wondering if the industry had its own way of becoming more efficient, if doing whatever means as far as working on becoming efficient, if maybe not on purpose, but the result of it would reduce the NOx emissions anyways. Are you following what I'm getting at here?
Yeah. So I'd say that's been most of my career for the last 20 years, has been going to plants and helping either reduce NOx emissions or make them more efficient, or both at the same time. Right? Yeah. So a lot of plants, I'd say, have either experimented with or they've just gone full into installing SNCR systems in the last 15 years. So any plant I would have gone to in the U.S. 20 years ago, I can almost guarantee you there would not have been an SNCR system in there for reducing NOx. I'd say maybe 80% of the plants out there now have an SNCR system, or there's a limited number that have SCR out there that are also trying to reduce emissions. So I'd say a lot of that's been brought about not necessarily by this good neighbor rule coming out, but by individual plants and individual states having their limits gradually reduced over time for ground level ozone reasons. Mm-hmm. So it's been happening. That's one thing. The other big shift that I'd say we've seen in the last 20 years is a lot more people shifting away from conventional fuels. So away from coal, away from pet coke. Certainly the last, I'd say 5 to 10 years, there's been a tremendous switch over to natural gas. Mm-hmm. And how you do natural gas in a kiln can also help with NOx emissions, depending on how you do it. But you see a lot of alternative fuels. So if there's a substance out there that can burn, I can almost guarantee you that a cement kiln somewhere in the world has tried to burn it. Right? You need a tremendous amount of fuel to melt rock. And what a lot of people have done over the last 20 years is move into all of these different alternative fuels that, in a lot of cases, can actually help reduce the emissions. So I'll tell you a story. I live in the Lehigh Valley. My office is here in Bethlehem, Pennsylvania. There's 5 cement kilns probably within a 20-mile radius of my house. And some good-meaning people from an environmental organization came to my house one day, and they were trying to get me to sign a petition to stop one of the local cement plants from burning tires. And I said, well, why don't you want them to burn tires? They're like, oh, they're evil. They pollute. Just think of all the black smoke that comes out. And I'll admit to being a little mean, because it was probably 20 degrees out, and I had them sit on my front stoop for a good half hour while I argued with them out in the cold. But I told them, look, when you burn a tire in a cement kiln, if you do it right, you reduce the NOx emissions, right? You reduce the amount of NOx that's coming out of the kiln. Everybody wins. The environment wins because you've helped reduce the NOx. You don't have this tire that's sitting out there, in a swamp somewhere breeding mosquitoes and all that other stuff. It's not going to catch on fire some other time and create all that black smoke. You're doing it in a controlled environment where it's reducing your environmental footprint, and you're able to use the iron and the steel belt that goes into the cement. Now we don't have to mine the iron from somewhere else. Oh, yeah. So it's a win-win-win. Why do you want to ban it? Well, because black smoke. And you're like, no, it's 2,800 degrees. There is no black smoke. There's not going to be anything coming off of it. And the only thing left is going to be the clinker coming out of the kiln. Uh-huh. So it's a lot of steps like that the industry has taken over the last 20 years, which also helps. It helps both ways. It helps reduce the plant cost. It helps the environment, and it to some extent improves the overall efficiency from the standpoint you don't need to mine other stuff to bring it into the plant.
Yeah, that's a cool story. Yeah. Is anyone out there? Are they actually burning tires?
Yeah. There's a lot of plants that burn them. I remember one plant. A lot of people are familiar with what a potato gun is.
Oh, right? Yeah.
There's a couple plants out there that have used essentially a giant potato gun that's big enough to shoot tires into a kiln.
Oh, that's cool.
Yeah, is there
videos of that on YouTube?
So I had seen videos from an R&D test, and it sort of reminds you of any movie where kids are outside playing baseball, right? Uh-huh. Because I watched this video one time of these guys, and they have this tire shooter, and basically this big compressed air cannon for shooting tires. And they've got it outside, and they're going to try it out because it's the first time they're using it. They want to see if it's actually going to be able to arc the tire into the kiln. So you have this shaky video, the guy with the camcorder sitting there recording everything. They're all sitting around like, oh, what pressure do we use on it? One guy's like, well, let's just crank it all the way up because we don't want it stuck in there because it's going to be a pain to get it out. Okay, well, how far do you think it'll shoot? Oh, I have no idea. Let's just crank it up and see the first time, right? You have the little shaky video, and they're standing back, and they're like, okay, fire, poof. And this tire just shoots out of this cannon and goes across the road and lands in the neighbor's yard. And you hear everyone like, run. It's like, it's like the kids with the baseball hitting it through the window. Nobody saw us do it. We got to hide.
Oh, man. Yeah. They can't use a conveyor or something, or what did they end up using?
So that's actually what they've used in a couple long wet kilns out there. So you shoot it uphill, and then it lands in the charge, and it slowly burns coming down. Mm-hmm. More modern kilns, there's all sorts of these special chutes that allow you to drop a tire in and try and keep the oxygen out. So you'll have like a double flap, so it'll allow the tire in, and then you'll have a second valve to let it fall down into the kiln system. There's a couple OEMs again out there that manufacture specialty machines to bring tires into the plant and drop them in and try and burn them well. Lord knows I've seen enough plants where it's gone wrong, but normally they try and make them burn pretty well.
Yeah. Well, you gotta try and figure it out, and then you don't know what's going to go wrong until you actually do it.
I got to tell you, there's a lot of other fuels out there. I mean, there have been plants out in the world that burn, leftover rice husk. When they're making rice and they're getting the grain, they have all the husk. They burn the rice husk. There's plants that burn seed corn that's expired. So all the corn that goes bad because they didn't get it planted in time or it's gotten a little wet, they'll burn that. I've seen sawdust, and I've seen demolition debris, and I've seen all sorts of different fuels used. But I got to say, my least favorite is I was at a kiln over in England back probably 16 years ago, back when they were having all the issues with mad cow. There were some plants in Europe that were burning cow. Like they were
the carcass.
Yeah, because you get for mad cow, you got to burn all the disease away. You can't just bury it because it gets into groundwater and whatnot. So they were basically making these giant hamburger facilities where they're grinding up the cow, and they had this fancy term for it: MBM, meat and bone meal. And they would grind it up and they would inject it in as a fuel in some of these plants because it would burn.
Wow.
Grossest thing I've ever seen, though, because the compressor that they'd fire it with would warm it all up and you get all the stuff start to melt and would plug the line. It was absolutely disgusting.
Man, who would have known? So this is to replace like the coal that they're burning and all that. That's pretty cool.
Trying to again, it's one of the if you look at the PCA's footprint or their plan for reducing carbon emissions, using more alternative fuels is one of those steps in the process of trying to replace traditional fossil fuels with essentially anything that'll burn.
Yeah, basically stuff that is going to get tossed away. So once again, I've said this on this podcast before, and this solidifies my opinion. Not that I need it, but I still think concrete's the most sustainable building material on earth. And again, we're using waste material to make cement. That's the kind of folks or smart people we got out there trying to figure out. So. And again, what I was getting at about the changes from what you mentioned before, the kiln technology changing in the 50s and changing in the 90s, is that is driven by companies want to be more efficient to make more money. It's driven by profit. We don't need the government to tell us, hey, you need to be more efficient or you need to emit less things into the air. I think we're figuring that out on our own. But anyways, that's my short rant for today, Peter. But I appreciate you coming on the show. I think this is a good spot to end today. I think you're someone we need to go back out to and have on the show again as we learn more about. I think learning about how cement is manufactured is fascinating. I spent a couple hours on YouTube looking at. I think there's a company it's in Africa that have these videos of their facility, and it's really in depth on how cement is made. And I can't remember what the company's name, but it seemed like a pretty big outfit. But they show you the steps that you were describing. So I encourage folks to go on YouTube and look that stuff up so you can kind of follow along what Peter was talking about. And it might make more sense for people like me that aren't as in tune with that whole process. But Peter, if folks want to reach out to you and learn more about what you do, and I'm sure we got some cement folks listen to the podcast that might need your help. What's the best way to get a hold of you?
Probably by email or reaching out through our website. So I'll give everyone my email. It's actually my last name. So Paone, Paonep. Last name, first initial, and that's at ZAP ECS.com. ZAPECS.com. That's ZAP Engineering and Construction Service. That's what it stands for.
Yeah, and we'll put that in the show notes as always. And folks, if you can go to our website, concretelogicpodcast.com, sign up for the newsletter. You'll get an email when this podcast comes out, and we'll have Peter's contact information on there as well. Peter, thanks for coming on the show today. Was happy that you could explain this in layman's terms for the most point.
Hopefully it was mostly layman's terms.
Mostly layman's terms, but it's great stuff.
It's hard when you start getting into all those acronyms and trying to follow the alphabet soup that's out there. But
yeah, I'm going to have to listen to this several times so I can get that done.
But I do also I have to say, the cement industry. So the Portland Cement Association runs a conference every year. That conference is normally the end of April or early May. So it's the IEEE-IAS/PCA Cement Industry Conference. I know, again, that's a mouthful, but that's because the Portland Cement Association co-sponsors it with the IEEE, which is the big electrical engineering association.
Okay.
There's a conference every year. I'm actually on the committee that helps put together the conference. And I'm actually in charge of some of the technical content for training. So I do a lot of training there. Certainly, if you're in the cement or concrete industries, it's a great resource for learning about the cement industry and for all the processes going on out there. So I can't say enough about all the work they do. I can't take all the credit for it. I only do a small bit, but if any of your listeners ever want to attend, that's a great conference to go to learn about the cement industry. Yeah,
and so that's coming up soon. And where's this year's conference?
This year's is actually in Dallas. So there's a whole bunch of things on LinkedIn about it. You can also look at the cement just look up cement conference on Google or any of your different search engines, and I'm sure you can find it.
Okay. All right. Yeah. And if you're attending that, look up Peter, and sounds like you're going to be doing some talks there as well, huh?
I will be. Yep.
All right. Well, Peter, I appreciate you coming on the show today, and we'll have to do it again.
Thanks so much, Seth.
Thank you for tuning in for another episode of the Concrete Logic Podcast. If you'd like to support the show, please visit our website, concretelogicpodcast.com, and click on the show support link. We welcome any amount you can provide. Your support enables us to continue to produce shows commercial-free and free of censorship. As we bring another episode to a close, let's enjoy some sweet tunes by the one and only Mike Dutton.
That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they tie their ties for their 9 to 5s,